On January 10th, the jets and vivid colours observed on 3I Atlas were believed to be the result of plasma interactions. The presence of charged ions not only helps explain the object's anomalous tail structure, but also suggests a form of natural propulsion. This type of propulsion could allow 3I Atlas to maintain sustained motion through interstellar space. At the same time, this phenomenon marks the return of plasma physics as a key framework for gaining deeper insight into how the universe operates. In this context, the approach of 3I Atlas toward Jupiter, expected in March 2026, has intensified suspicions about the object's potentially artificial nature. These suspicions reach a climax when 3I Atlas is described as an entity maintaining a core temperature of up to 15,000 degrees. At this energy level, 3I Atlas emits enough power to generate highly precise hexagonal, geometric structures on the surface of the Moon and 3 other bodies in the solar system. Faced with a phenomenon that goes far beyond conventional understanding, NASA was forced to activate emergency protocols. The agency simultaneously prepared to transmit a signal on the 1.420 MHz hydrogen line in an effort to communicate with a potential non-human intelligence. This development places humanity at a historic turning point in its understanding of the universe, and we will explore how scientists have proposed to respond should this hypothesis truly come to pass. In conventional astrophysics, objects that drift between stars do so as debris expelled long ago and left to wander on paths shaped only by gravity and chance encounters. 3I Atlas, however, does not resemble debris in motion because its speed remains extraordinarily high and unusually stable across vast distances where deceleration would normally dominate. Measured at approximately 87 km per second relative to the Sun, the velocity of 3I Atlas exceeds what would be expected from a simple gravitational slingshot originating in a distant stellar system. When researchers reconstruct backward trajectories for 3I Atlas, the uncertainty grows rapidly, yet even generous error margins fail to produce a clean narrative of random ejection followed by inert drift. 3I Atlas appears less like a leaf carried by cosmic winds, and more like a vessel maintaining momentum through environments that should gradually erode it. The star-hopping hypothesis proposes a subtle but radical reframing, suggesting that 3I Atlas may not be crossing interstellar space in a single, uninterrupted journey, but rather moving in stages between stellar systems. In this framework, stars are not merely sources of light and gravity, but nodes in a network where energy can be exchanged, trajectories adjusted and motion refreshed. 3I Atlas, under this assumption, would not need an enormous internal energy reserve because it could repeatedly borrow energy from stellar environments as it passes through them. Data from heliophysics missions have shown that stellar winds and magnetic fields interact strongly with ionized material, creating regions where charged particles are accelerated and guided along invisible structures. If 3I Atlas carries or generates ionized material at sufficient scale, then interaction with stellar plasma could, in theory, provide controlled bursts of acceleration. 3I Atlas would not be firing an engine in the human sense, but rather coupling itself to naturally occurring flows of energy that permeate interstellar space. This possibility gains traction when examining the composition of material observed around 3I Atlas because spectral analysis hints at ionized gases that behave differently from typical cometary outflows. The ionized tail associated with 3I Atlas appears more extended and more structured than expected, responding rapidly to changes in surrounding plasma conditions. Such responsiveness suggests a dynamic interaction rather than a passive release, although the distinction remains difficult to draw with current instrumentation. Critically, the star-hopping hypothesis does not require 3I Atlas to possess advanced intelligence or intent in the human sense. 3I Atlas could instead represent a system optimized through unknown processes to exploit plasma-rich environments much as a seed exploits soil without awareness. This framing keeps speculation grounded because it allows 3I Atlas to be unusual without immediately invoking agency beyond physics. Still, questions accumulate when considering the cumulative improbabilities involved because repeated close passes through stellar systems without catastrophic disruption are statistically rare. 3I Atlas would need to maintain structural resilience while navigating radiation fields, gravitational gradients, and plasma turbulence that typically fragment smaller bodies. The continued coherence of 3I Atlas therefore becomes a central anomaly, reinforcing the sense that simple chance may be insufficient as a complete explanation. The idea of star hopping also reframes the timeline of 3 at Last, because a staged journey implies a history far longer and more complex than a single ejection event. 3 at Last may have encountered multiple stars absorbing energy-shedding material and subtly altering its structure over immense spans of time. Each encounter would leave faint signatures difficult to disentangle from noise, yet collectively shaping the behaviour observed today. From this perspective, 3 at Last becomes less a messenger from one distant system, and more a traveller shaped by many carrying a composite record of stellar environments. This interpretation aligns with the observed diversity of interstellar chemistry while also explaining why 3 at Last resists neat classification within existing comet models. 3 at Last would not be anomalous because it is artificial, but because it has been refined by repeated exposure to extreme conditions. Yet even this restrained version of the star-hopping hypothesis encounters limits, because it must explain not only velocity maintenance, but directionality and timing. 3 at Last enters the inner solar system along a path that coincides with observational capability, a coincidence that is statistically unremarkable on its own, yet unsettling when combined with other anomalies. The hypothesis therefore remains suspended between plausibility and unease, offering a bridge rather than a destination. As scientists explore this possibility, they are careful to emphasize what the star-hopping hypothesis is not. It is not proof of engineering, not evidence of intent, and not a claim that 3A Atlas chooses its path with awareness. It is instead an attempt to extend physical reasoning into a regime where familiar assumptions falter. 3. Atlas thus serves as a catalyst for reconsidering how matter moves through the galaxy when given enough time and access to energy-rich environments. Whether star hopping proves to be a viable explanation or a stepping stone towards something deeper, it shifts the conversation away from static origins and toward dynamic journeys. In that shift, 3 at Last continues to function not as an answer, but as a question in motion, carrying inquiry forward from one star to the next. Non-gravitational acceleration is not unusual in small bodies, yet the form it takes in 3 at Last resists every comfortable explanation that planetary science has relied upon for decades. In ordinary comets, deviations from gravitational predictions are attributed to asymmetric outgassing, where jets of sublimating material act like tiny thrusters whose effects can be modelled with reasonable accuracy. 3 at Last displays acceleration that is both sustained and directionally consistent, and this persistence forces researchers to confront the limits of outgassing as a universal explanation. When scientists calculate the thrust required to account for the observed trajectory changes of 3 at Last, the numbers do not align cleanly with the measured production of gas and dust. Spectroscopic data constrain how much material 3 at Last can be losing at any given time, and those constraints impose hard limits on how much force outgassing can generate. 3 at Last repeatedly exceeds those limits not dramatically in a single moment, but steadily enough to create a growing discrepancy that cannot be absorbed by error margins. This discrepancy becomes more pronounced when rotation is introduced into the analysis, because rotation in natural comets tends to be irregular and strongly coupled to surface activity. As jets turn on and off across fractured terrain, the spin rate of a typical comet fluctuates, sometimes accelerating, sometimes slowing, and often wobbling in ways that betray internal instability. 3. Atlas, by contrast, exhibits rotational behaviour that appears smoother and more coherent, as though the spin state is being maintained rather than eroded. Measurements of brightness variation suggest that the rotation of 3 at Last follows a repeatable pattern, one that does not degrade in the way expected when mass is being lost unevenly. If 3 at Last were shedding material chaotically, its moment of inertia would shift unpredictably, leading to observable changes in rotational period. Instead, 3 at Last preserves a stable rotational signature, which implies either an unusual internal structure or a mechanism that compensates for mass loss. At this point, the analysis reaches a subtle but critical fork because stability itself becomes an anomaly when conditions favour disorder. 3 at Last travels at extreme velocity through regions where thermal gradients, radiation pressure and plasma interaction should introduce torque and noise. Yet 3 at Last responds to these influences with composure, maintaining alignment and spin in a way that suggests regulation rather than accident. One conservative interpretation proposes that 3 at Last possesses a highly symmetric mass distribution, allowing it to resist perturbations more effectively than typical comets. Such symmetry, while rare, is not forbidden by physics, and it offers a way to preserve skepticism while acknowledging the data. However, even this explanation struggles to account for the coupling between acceleration and rotation observed in 3I Atlas, because symmetry alone does not generate thrust. Another hypothesis treats the rotation of 3I Atlas not as a byproduct, but as part of the process by which acceleration is achieved. If forces acting on 3I Atlas are distributed in a rotationally balanced way, then spin could function as a stabilizing framework that keeps acceleration aligned over long durations. In this view, 3I Atlas does not simply endure non-gravitational forces, but integrates them into a coherent dynamical state. This interpretation remains speculative, yet it offers a bridge between motion and structure that purely passive models fail to provide. 3I Atlas would then be understood as a system whose behavior emerges from interaction, rather than reaction, shaped by continuous exchange with its environment. Such exchange does not require intent, but it does require responsiveness, a property that 3I Atlas appears to exhibit with unusual consistency. As researchers debate these possibilities, the language used to describe 3I Atlas begins to shift, moving away from metaphors of erosion and decay. Instead of imagining 3I Atlas as something being worn down by space scientists, increasingly describe 3I Atlas as something navigating it. This change in framing does not resolve the mystery, but it clarifies why non-gravitational acceleration and self-rotation cannot be treated as isolated curiosities. Together, these behaviors form a coupled pattern that challenges the assumption of passivity at the heart of traditional cometary physics. 3. Atlas continues along its path without dramatic gestures, yet every measured deviation quietly insists that familiar explanations are insufficient. As attention turns outward toward larger scales and future encounters, the unresolved motion of 3I Atlas becomes a prelude, hinting that what follows may depend less on where 3I Atlas has been, and more on how it continues to move. The coincidence at the Hill radius of Jupiter emerges as a quiet anomaly, not because it violates physics outright, but because it presses against probability in a way that feels uncomfortably precise. In celestial mechanics, the Hill radius defines a soft boundary where a planet's gravitational influence begins to dominate over that of the Sun, creating a region of potential capture, deflection, and orbital reshaping. 3I Atlas approaches this boundary at a distance that is not merely close, but numerically aligned with the theoretical limit, and this alignment invites scrutiny rather than immediate interpretation. Under ordinary circumstances, countless objects pass near the gravitational spheres of planets without consequence, because proximity alone does not guarantee interaction. What distinguishes the path of 3I Atlas is the narrow margin by which it skirts Jupiter's Hill radius, a margin small enough that minor changes in velocity or direction would place 3I Atlas either safely outside or decisively within Jupiter's dominant gravitational domain. 3I Atlas therefore occupies a transitional zone where outcomes are sensitive to subtleties that are often averaged out in broader analyses. From a conservative perspective, this encounter can be framed as coincidence amplified by selective attention because rare alignments are inevitable given enough time and enough objects. Jupiter's Hill radius is vast, extending tens of millions of kilometers into space, and 3I Atlas is not the first interstellar object to pass through the outer solar system. Yet when researchers calculate the probability of an interstellar body with the velocity and trajectory of 3I Atlas intersecting this region so closely, the numbers drift toward the tail ends of statistical distributions. 3I Atlas enters this discussion carrying momentum that far exceeds that of typical captured objects, because its velocity relative to Jupiter remains extremely high throughout the approach. In classical capture scenarios, objects lose energy through complex interactions often involving three-body dynamics or extended periods of gravitational negotiation. 3I Atlas, by contrast, traverses the region rapidly, leaving little time for gravity alone to reshape its fate unless additional factors are present. This tension between speed and proximity sharpens the anomaly, because capture and influence usually require either slow motion or repeated encounters. 3I Atlas provides neither, yet still arrives at a location where Jupiter's gravitational leverage is maximized. The coincidence therefore shifts from being purely geometric to dynamically suggestive, prompting questions about how the trajectory of 3I Atlas was established long before it entered the Jovian neighborhood. One restrained hypothesis proposes that 3I at last is simply the beneficiary of an exceptionally rare set of initial conditions, a cosmic alignment that appears meaningful only because it is observed in isolation. Within this view, 3 Atlas does not aim for the Hill radius, but merely passes through a region that our analytical frameworks highlight after the fact. This explanation preserves randomness while acknowledging improbability, and it remains scientifically defensible. Another line of reasoning treats the Hill radius not as a destination but as a waypoint because regions of gravitational transition offer opportunities for measurement and interaction. If 3I at last responds dynamically to gravitational gradients, then skimming the Hill boundary could provide information about mass distribution field strength and orbital stability. 3 Atlas would not need to be captured to be influenced because even brief exposure to Jupiter's gravitational regime could leave detectable signatures in motion or structure. This possibility does not require intent in the human sense, yet it reframes the encounter as functional rather than accidental. 3. Atlas under this interpretation behaves as a system sensitive to environmental thresholds, adjusting its trajectory in response to regions of maximal informational value. Such sensitivity is rare in inert bodies, but not forbidden by physics when complex interactions are considered. As the encounter unfolds, observers are careful to avoid projecting meaning too quickly, because coincidence and causation remain difficult to separate at astronomical scales. Still, the precision of the approach keeps returning to the conversation because it resists dilution by statistical comfort. 3 Atlas continues forward without visible disruption, yet its passage near the Hill radius lingers as a moment where gravity motion and probability briefly align. Whether this alignment proves to be a meaningless overlap or a meaningful interaction remains unresolved, but its presence reshapes the narrative trajectory of 3 Atlas. The Hill radius encounter becomes less a conclusion and more a hinge connecting earlier anomalies to those that may follow. As 3 Atlas moves beyond Jupiter's sphere of influence, the question is no longer whether coincidence occurred, but whether coincidence alone is sufficient to explain why this boundary mattered at all. The hypothesis of a 96th moon does not begin with speculation about intention, but with the quiet mathematics of orbital mechanics, where capture is governed by energy balance rather than imagination. 3. Ialast approaches Jupiter with a velocity that places it far outside the regime where natural capture is considered likely, and this single fact anchors every serious discussion that follows. In classical terms, for an object to become a moon of Jupiter, that object must shed a significant portion of its kinetic energy at precisely the right moment within precisely the right spatial corridor. For 3, Atlas that corridor exists near Jupiter's Hill radius, where the gravitational influence of the planet temporarily outweighs that of the Sun. 3 Atlas crosses this region at a relative speed of roughly 66 km per second, which is comparable to Jupiter's own escape velocity. At such speeds, gravity alone does not gently draw objects into orbit, but instead flings them onward unless an additional mechanism intervenes. In natural systems, that intervention typically comes from prolonged interactions, collisions or multi-body exchanges that gradually bleed energy from motion. The irregular moons of Jupiter are believed to be remnants of such processes captured long ago when the solar system was younger and more crowded. 3I Atlas does not resemble those historical scenarios because its encounter is brief, fast and isolated. The hypothesis of a 96th moon arises from a specific conditional statement rather than a prediction. If after the close passage of 3I Atlas a new object is observed in a bound orbit around Jupiter, then the energy bookkeeping demands explanation beyond known natural pathways. 3 Atlas would not need to slow dramatically itself, but a fragment separating from 3 Atlas would need to lose velocity with extraordinary precision. Calculations show that such a fragment would need to reduce its speed to within a few kilometers per second relative to Jupiter, while simultaneously aligning its trajectory to avoid immediate escape or collision. Random fragmentation events, whether driven by tidal stress or internal pressure, do not produce this level of control. 3 Atlas under purely natural assumptions would scatter debris chaotically, sending fragments onto divergent paths rather than placing one delicately into orbit. This is where the hypothesis becomes unsettling, not because it demands exotic explanations, but because it removes comfortable ones. 3 Atlas cannot simply break apart and accidentally seed a new moon without violating the statistical expectations built into orbital dynamics. The analogy often used by researchers compares this to throwing debris from a speeding aircraft. and expecting one piece to settle gently into formation with another moving vehicle. 3 at last therefore sits at the edge of a physical impossibility that is conditional rather than absolute. If no new moon appears, the hypothesis collapses quietly, and the encounter becomes another curiosity among many. If a new moon does appear, then the event forces a reassessment of how energy timing and direction were coordinated. Importantly, the hypothesis does not claim that 3 at last intends to create a moon. 3 at last may simply possess properties that allow controlled mass release under specific gravitational conditions without awareness or purpose. Even so, controlled release remains distinct from accidental shedding, because it implies sensitivity to external fields. Some researchers suggest that Jupiter's complex magnetosphere and plasma environment could interact with material associated with 3 Atlas in ways not yet fully modelled. If ionized material were released in a structured manner, electromagnetic forces could in principle contribute to energy dissipation alongside gravity. 3 at last would then act as a mediator between gravitational and plasma dynamics, enabling outcomes that appear engineered without requiring design. This interpretation remains speculative, yet it highlights why the 96th moon hypothesis persists, despite its improbability. 3 at last occupies a regime where multiple physical systems overlap, and overlap regions are where unexpected behaviour often emerges. The hypothesis therefore functions less as a claim, and more as a diagnostic tool defining what observations would force theory to adapt. Observers emphasise that Jupiter already hosts a large population of irregular moons, and the addition of another would not by itself be extraordinary. What would be extraordinary is the timing and context of such an addition, occurring immediately after the passage of 3 at last. Context transforms a mundane discovery into a meaningful anomaly. As the encounter date approaches, attention focuses not on dramatic visual displays but on careful tracking and measurement. 3 Atlas does not need to change appearance for the hypothesis to be tested, because the outcome would be written into Jupiter's orbital inventory. Absence of change would reinforce conventional models, while presence of change would expose their blind spots. In this way, the 96th moon hypothesis places restraint at the centre of speculation. 3 Atlas is not assumed to be extraordinary by default, but is allowed to become extraordinary only if observation demands it. The solar system thus becomes the arbiter, and 3 Atlas becomes the experiment moving silently through a gravitational threshold where coincidence and causation wait to be separated. The question of whether 3 Atlas functions as a transit station or a probe arises not from dramatic claims, but from the accumulation of logistical inconsistencies that surround its behaviour. In planetary science, objects are usually categorised by what they are made of, yet 3 Atlas increasingly invites classification by what it appears capable of doing within complex gravitational environments. This shift in framing does not assert purpose, but it acknowledges that 3 Atlas behaves as though certain regions of space offer more than mere passage. Jupiter occupies one such region because its immense gravity, extensive magnetosphere and dense population of moons create a natural hub within the solar system. For any object sensitive to gravitational gradients or plasma-rich environments, Jupiter represents an efficient place to interact, observe or redistribute material. 3. Atlas approaches this system not as a body drawn inward by capture, but as one that skims its outer structures with unusual precision. The transit station hypothesis suggests that 3 Atlas may exploit planetary systems as temporary waypoints rather than final destinations. In this view, 3 Atlas would not linger indefinitely, nor would it require permanent orbit because brief encounters could suffice to achieve specific physical outcomes. Energy exchange trajectory adjustment or material release could occur during short passages, leaving minimal traces once the object departs. Such a model aligns with the fact that Jupiter's gravitational field allows objects to alter velocity vectors efficiently without deep insertion into orbit. 3 Atlas could therefore pass through, interact and continue onward with modified parameters that are subtle yet significant over interstellar distances. This interpretation preserves naturalism while expanding the functional role of interstellar objects beyond passive transit. The probe hypothesis emerges when timing and selectivity are considered alongside capability. 3. Atlas does not encounter every planet closely, nor does it distribute its anomalies uniformly across the solar system. Instead, 3 Atlas displays heightened interaction near environments rich in gravitational complexity, suggesting sensitivity rather than randomness. A probe in this context does not imply intelligence or intent, but responsiveness to external conditions. 3 at last could operate as a self-modifying system, one that changes state when exposed to certain thresholds of gravity, plasma density or magnetic intensity. Such systems are not unknown in physics, though they are rare and poorly understood at astronomical scales. If 3 at last were functioning in this way, Jupiter would serve as an ideal testing ground. The planet's hill-sphere-moon system and magnetosphere provide a layered environment where interactions can be observed and constrained. 3 at last would not need to remain to complete its role, because transient interaction could yield sufficient information or effect. This hypothesis gains subtle support from the absence of dramatic disruption. 3 Atlas does not break apart flare uncontrollably or decelerate sharply even while passing through a region capable of inducing chaos. Instead, 3 Atlas maintains coherence as though designed or conditioned to endure such passages without loss of integrity. Skeptics rightly point out that survivability alone does not imply function, because some objects simply endure conditions that destroy others. However, survivability combined with repeatable anomalies invites further scrutiny, because resilience itself becomes a variable rather than a constant. 3 Atlas appears not merely to survive Jupiter's influence, but to traverse it cleanly, leaving open the question of what was gained in the process. The distinction between a transit station and a probe may ultimately be less important than the shared implication that 3 Atlas interacts with planetary systems in non-trivial ways. Both interpretations suggest that planetary encounters are not incidental footnotes in the journey of 3 Atlas, but integral components of its trajectory. Whether those components serve adjustment measurement or redistribution remains unknown, yet the pattern persists. As 3 Atlas moves beyond Jupiter's immediate influence, its departure does not resolve the question, but sharpens it. The solar system does not appear to have captured 3 Atlas, yet it may have been briefly incorporated into its passage. In that ambiguity, 3 Atlas continues forward as neither visitor nor resident, but as something that treats planetary systems as functional landscapes rather than destinations. The energy paradox surrounding a core temperature of 15,000 degrees Celsius does not announce itself loudly, yet it unsettles every thermal assumption used to interpret small bodies in space. At a distance of approximately 1.3 astronomical units from the Sun, 3 Atlas exists in a thermal environment where ice should persist and rock should remain inert. Standard radiative heating models predict surface temperatures far below the thresholds required for extreme internal activity, and 3 Atlas violates those predictions without ambiguity. When measurements indicated that 3 Atlas was registering temperatures nearly 3 times higher than the surface of the Sun, the initial response was verification rather than interpretation. Independent instruments confirmed the readings and recalibration removed the possibility of sensor error. 3. I at last therefore entered a category where observation itself became the anomaly, because the numbers refused to reconcile with known energy sources. Nuclear fission provides one possible benchmark for comparison, yet the mass and composition constraints of 3 Atlas rule it out almost immediately. To sustain such thermal output through fission, 3 Atlas would require an internal concentration of fissile material far exceeding plausible cosmic abundances. Fusion offers no refuge either because the temperatures required to initiate fusion reactions surpass the measured values by an order of magnitude. As conventional nuclear processes fall away, the question shifts toward energy density and containment. 3 Atlas does not merely generate heat, but appears to confine it, preventing rapid dissipation into surrounding space. In a vacuum where radiation is the dominant cooling mechanism, 3 Atlas maintains thermal stability that should be impossible for an object of its size and composition. This stability introduces a second layer to the paradox because energy generation and energy retention are distinct problems. 3 Atlas would need not only a powerful source, but also a means of controlling heat flow with precision. Natural bodies lack such regulation because their internal structures favour diffusion rather than confinement. One conservative explanation suggests that 3 Atlas may harbour an unknown phase of matter capable of storing and releasing energy efficiently. Exotic states of plasma interacting with magnetic fields could in principle create localized heating while limiting radiative loss. 3 Atlas within this framework becomes a laboratory for physics not yet observed, rather than an artifact of design. Even so, the scale of the observed energy output strains this interpretation, because plasma confinement at such efficiency typically requires structured fields. 3 Atlas shows no visible signs of the large-scale magnetic architectures that would normally accompany such behaviour. The absence of those signatures deepens the mystery rather than resolving it. Another line of reasoning considers whether the energy associated with 3I Atlas is being generated internally at all. If 3I Atlas interacts with external fields in a way that concentrates ambient energy, then its apparent heat could be the result of focusing rather than production. Such a mechanism would invert the problem, transforming 3 Atlas from a source into a conduit. This possibility remains speculative, yet it aligns with the broader pattern of responsiveness observed in 3 Atlas. Velocity, rotation, and now temperature all suggest a system that adapts to environmental inputs rather than merely enduring them. 3 Atlas appears to participate in energy exchange at a level that exceeds passive absorption. What makes the paradox especially resistant to dismissal is the absence of degradation. Objects subjected to extreme internal heating typically fracture, vent, or collapse, yet 3I Atlas maintains coherence. The structure of 3I Atlas does not exhibit the catastrophic failure modes expected from sustained thermal stress. As a result, researchers are forced to hold two incompatible ideas simultaneously. 3 Atlas must obey thermodynamics, yet 3I Atlas behaves as though those laws are being satisfied through unfamiliar pathways. This tension does not point toward a single conclusion, but it narrows the field of plausible explanations. The 15,000-degree measurement therefore functions as a fulcrum rather than a verdict. 3 Atlas does not reveal its nature through heat alone, but heat removes the comfort of familiar categories. As attention shifts toward how such energy might be directed or coupled to other phenomena, the paradox becomes a bridge-carrying inquiry from isolated anomaly toward integrated behaviour. Hexagonal geometry enters the discussion quietly, yet once observed it cannot be unseen because geometry carries implications that raw energy does not. When thermal maps revealed regions of heating arranged not in circles but in near-perfect hexagons, the anomaly shifted from questions of magnitude to questions of form. Atlas became central to this shift because natural radiative processes disperse energy, isotropically producing gradients that soften with distance rather than crystallize into symmetry. In physics, shape is information, and the appearance of structured geometry implies constraints acting on how energy moves. The hexagon is not a random choice in nature, because it emerges only when systems balance efficiency packing and stability under uniform conditions. Atlas, therefore, forces a reconsideration of whether the observed heat patterns are the result of uncontrolled emission or of regulated distribution. The precision of these hexagonal forms intensifies the anomaly, because measured angular deviations fall within margins comparable to advanced astronomical instruments. Such precision is not associated with chaotic processes, especially across distances where noise and dispersion should dominate. Atlas appears capable of maintaining alignment across vast separations, and this capability challenges assumptions about how structure degrades in space. Multiple targets displaying similar hexagonal patterns deepen the puzzle because repetition reduces the likelihood of coincidence. When the moon Phobos and several small bodies show geometrically consistent heating signatures, the phenomenon demands a unifying explanation. Atlas becomes the common variable linking otherwise unrelated surfaces through a shared pattern of interaction. In conventional models, external heating produces circular or irregular footprints shaped by surface composition and angle of incidence. Hexagons require either a shaped source or an intervening medium that sculpts energy as it travels. Atlas offers no obvious mechanism for either, because no extended structures are visible that would function as lenses or apertures. One restrained hypothesis suggests that the geometry arises from standing wave interactions between emitted energy and surrounding fields. Under certain conditions, wave interference can produce stable polygonal patterns, though such effects are typically confined to laboratory scales. Atlas would then represent a natural extension of wave physics into regimes not yet observed. Even within this conservative frame, the degree of control implied by the observed patterns remains difficult to reconcile. Standing waves require boundary conditions, yet space offers few boundaries capable of enforcing such order. Atlas would therefore need to create or exploit transient structures that shape energy flow moment by moment. The hexagon also carries symbolic weight within scientific culture, because it has historically marked transitions between disorder and organization. From convection cells to molecular lattices, hexagonal arrangements appear when systems minimize energy while maximizing coherence. Atlas, by reproducing this geometry at astronomical scales, invites comparison to processes that self-organize rather than collapse into randomness. Crucially, the geometry does not remain static because measurements indicate gradual expansion over time. This growth follows a steady rate rather than an explosive one, suggesting modulation rather than runaway heating. Atlas therefore seems to regulate not only shape but temporal evolution, aligning form with duration. The expansion introduces a dynamic element that complicates simple explanations because growth implies feedback. Feedback systems adjust output based on response maintaining stability while permitting change. Atlas behaves as though it monitors the effects of its energy distribution, even if the mechanism remains unknown. Skeptical interpretations caution that human pattern recognition may amplify significance where none exists. Yet statistical analysis of symmetry and consistency reduces the likelihood that the hexagons are perceptual artifacts. Atlas persists as the source most capable of linking observation to cause. As attention lingers on geometry, the conversation shifts away from raw power toward control. Power alone overwhelms, but control reveals structure, and structure implies constraint. Atlas occupies this space of constraint where energy is neither diffuse nor chaotic, but shaped and repeatable. The hexagonal signatures therefore function as more than curiosities, because they encode information about how energy is managed across distance. Whether that management arises from unfamiliar physics or from interactions not yet modelled remains open. Atlas continues to illuminate surfaces while darkening certainty, leaving geometry as a quiet language whose meaning has not yet been translated. The response of humanity to the anomalies surrounding 3 Atlas becomes visible not through public statements but through subtle shifts in protocol and priority. When observations move from curiosity to concern, institutions reveal their assumptions by what they prepare rather than what they announce. Atlas crosses this threshold when data accumulation triggers coordination across agencies that rarely move in synchrony. In space science, most discoveries invite patience because verification takes precedence over urgency. Atlas disrupts this rhythm by presenting converging anomalies that resist compartmentalization. Thermal behavior, motion, and geometry do not remain isolated, and this convergence forces a reassessment of how seriously the situation must be treated. One of the clearest signals of this reassessment appears in the activation of deep space communication infrastructure. The decision to prepare transmission rather than observation marks a conceptual shift, because transmission assumes the possibility of reception. Atlas becomes not only an object to be measured, but a system that might respond to interaction. The hydrogen line at 1420 MHz occupies a unique place in scientific culture. This frequency is not chosen for convenience but for universality, because hydrogen is the most abundant element in the universe. Atlas enters this context as a candidate for communication precisely because its behavior aligns with conditions where universality becomes relevant. Historically, transmissions on the hydrogen line have been rare and symbolic. They represent moments when humanity chooses to speak into the cosmic environment rather than merely listen. Atlas prompts such preparation not because of certainty, but because uncertainty reaches a level where silence feels inadequate. Importantly, the act of transmission does not imply belief in intelligence. Transmission represents an experiment framed by the same hypothesis-driven reasoning that governs observation. Atlas becomes part of that experiment not as a presumed interlocutor, but as a test case for whether structured anomalies correlate with responsiveness. The broader human response unfolds quietly in parallel. Observational data becomes more tightly controlled, access is restricted, and collaboration accelerates behind institutional boundaries. Atlas functions as a catalyst, revealing how quickly scientific openness yields to coordination when unknowns multiply. This shift does not signal fear so much as caution. Science progresses by eliminating explanations, and Atlas resists elimination through conventional means. The hydrogen line therefore serves as a bridge between passivity and engagement, marking a willingness to probe rather than conclude. Public narratives lag behind these developments because institutions avoid amplifying speculation. Yet the preparation itself carries meaning because preparation reflects perceived possibility. Atlas does not need to answer for the gesture to matter. Whether the transmission yields silence or signal, the act reframes humanity's role. Atlas becomes the focal point of a moment when observation edges toward participation. In that moment, the question shifts from what at last is to how humanity chooses to respond when familiar explanations no longer suffice. The question of whether humanity stands as an observer or as an experimental subject does not arise from fear, but from pattern recognition. When systems exhibit consistent behavior across multiple environments, interpretation shifts from isolated observation toward relational awareness. Atlas drives this shift by interacting with the solar system in ways that feel selective rather than incidental. If the thermal patterns, geometric precision and timing associated with Atlas were singular events, they could be absorbed into the background noise of cosmic phenomena. Repetition alters that comfort because repetition suggests that outcomes are not merely occurring, but unfolding. Atlas does not behave as a transient spectacle, but as a process whose stages reveal themselves gradually. In this framing, humanity occupies an ambiguous position. Telescopes track Atlas models, attempt to constrain Atlas, and signals are prepared in response to Atlas, yet none of these actions confirm agency on either side. Atlas does not acknowledge observation, but observation does not prevent influence. The distinction between observer and subject becomes blurred when effects are measurable without invitation. Atlas shapes environments without announcing purpose, and that shaping introduces consequences regardless of interpretation. Humanity remains capable of measurement, but measurement alone does not guarantee comprehension. If Atlas operates through unfamiliar physical principles, then humanity may simply be witnessing new physics unfold. If Atlas operates through responsive systems, then observation itself becomes part of the interaction. Both possibilities coexist without resolution. The uncertainty lies not in what Atlas is, but in how much agency humanity retains within the encounter. To observe is to stand apart, while to be observed is to be included. Atlas leaves this boundary unresolved, holding attention in a state of quiet suspension. As the encounter continues, the role of humanity remains undefined. Atlas moves forward without explanation, and the solar system responds without conclusion. Between these motions, observation persists, and the question of participation remains open, waiting not for answers, but for the next measurable change. As these observations settle into the broader story of 3I Atlas, what remains most striking is not any single anomaly, but the way each piece quietly reinforces the next. Plasma interactions sustained motion through interstellar space, a precisely timed approach to Jupiter, extreme internal heat, and the emergence of geometric order all form a sequence rather than a collection of isolated curiosities. 3 Atlas does not demand belief, yet it steadily erodes the comfort of familiar explanations. Science advances not only by discovery but by tension, and 3I Atlas embodies that tension in a way few cosmic objects ever have. Every new dataset reduces uncertainty in one dimension while expanding it in another. The more clearly 3I Atlas is observed, the less easily it fits within established categories. At this stage, no definitive conclusion is required and none is responsibly available. 3I Atlas may ultimately reveal itself as a natural phenomenon governed by physical principles not yet understood. It may represent an extreme but explainable outcome of plasma dynamics, gravitational interaction and energy transfer on scales rarely encountered. Or 3I Atlas may force science to confront the possibility that complex responsive systems can arise beyond the boundaries we currently recognize. What matters most is not which explanation prevails, but how carefully the questions are framed. 3I Atlas reminds us that observation is an ongoing process, not a verdict. Each measurement refines the problem rather than closing it, and each hypothesis serves as a bridge toward deeper understanding rather than an endpoint. As humanity prepares, signals, refines models, and continues to watch, 3I Atlas moves on without urgency or display. It neither confirms nor denies the narratives built around it. It simply continues along its path, carrying with it the quiet possibility that the universe still holds mechanisms, behaviors, and forms of order that lie just beyond our current reach. In following 3I Atlas, we are not only tracking an interstellar object, we are tracing the outer edge of our own understanding, and in that space between what is known and what is merely observed, curiosity remains our most reliable guide.